We are now recording. All right. So let me share this. Screen broadcast, start broadcast. Okay. Like I say, these are now uploaded. Sorry that didn't go up there before. I just noticed that I haven't made it. So too much stuff happening here. All right. So backpropagation. Backpropagation was historically, this was actually a very important algorithm. The perceptron algorithm that we started with, Rosenblatt's perceptron and the McCulloch-Pitts model with the perceptron learning rule, was thought to be very, very powerful and was going to be a new era in computing in the 1960s. And toward the end of the 70s, early 80s, there was a book by Minsky and Papert called Perceptrons, which pointed out that they cannot solve the XOR problem. And in fact, that there are large numbers of problems that can't be solved by perceptrons, and basically killed that field. It just died overnight in response to the Minsky and Papert papers, and subsequently a book which went through this. And it really showed that there was a fundamental limitation in this. And everybody sort of knew that multi-layer things could do better, but nobody really had the mathematics to do it and hadn't figured it out. And then in, I guess, the early 80s, there was a series of papers, and there's some question as to who actually did this, but there was a book by Rumelhart Hinton did the original papers on this. And that was the book, and it was called Parallel Distributed Processing. It was actually two books. And it went through a number of different algorithms, but the key element in this was the backpropagation algorithm. Now, the backpropagation algorithm had probably been discovered in several different formats. It probably existed for at least 10 to 15 years prior to that book. Blanking on the name of the person who was credited with it, but it's basically the chain rule, and so there will be things that look like backpropagation in many different fields, but the application to multi-layer, what were then called multi-layer perceptrons or multi-layer networks, was really restarted by the perceptrons book, and that was and that sort of led to a approximately 15-year period of great excitement around this algorithm, looking both at its power and at its weaknesses. And it also led to the development of several other algorithms at the same time, many of which we'll go through in the rest of this class. It kind of fell apart a little bit at the end of the 90s when people sort of realized that the backpropagation, although it was very successful at solving certain types of problems, also had significant limitations and was in most cases not provably able to find the right answer. Although you could not in many cases even prove that it converged. And so it was then viewed as sort of a black box that didn't give all that much understanding. And while it could solve some problems, there generally were ways of solving these problems that were better. And in fact, many of the problems, several of the problems that have been considered triumphs of backpropagation were shown to be trivial. One of those was what was called the truck backer upper problem, which was, I believe, one of the examples in the original PDP book, Parallel Distributed Processing. And the truck backer upper was the idea that if you have a semi-truck, so that the cab of the truck is separated from the rest of the tractor trailer, and you have to basically you have to back it up. It's facing the wrong way in a loading dock, and you basically have to turn it around to get it to face the right way in the loading dock. And you can imagine the cab goes, you turn the steering wheel one way, the cab goes one way, the back goes the other. It's a difficult problem for humans. And of course, very skilled truck drivers have to train for long periods of time in order to be able to do this. So this was thought to be a hard problem, and it was shown that you could solve this through backpropagation. And that was considered one of the triumphs of backpropagation. Until at the end of the 90s, somebody pointed out that the actual mathematics of the truck backer upper problem are really trivial and can be solved essentially with a linear network. And it's just that humans were unaware of that. And so that humans spent a long time trying to figure this out and sort of do it by feel. But in fact, a reasonable mathematical algorithm should have been able to find this in 1 or 2 steps. There were a few other triumphs of these multi-layer perceptrons. At the time, there was the ability to play backgammon. Dave Turetsky and his group had worked on that for a long time. And then there were, and there was NetTalk, which is mentioned in the Haken book, which was a speech synthesis, not a very good speech synthesis by current standards, but it was able to do some speech synthesis. But in the end, everybody sort of decided that this was just another statistical method, and that approach was led by one of the professors at MIT by the name of Michael Jordan. He's now at Berkeley, and he had looked very carefully at the relationship between many of these algorithms and classic control theory, as well as classical statistical methods, and shown that the statistical methods were more robust, easier to understand, and more likely to get you the right answer. So the thing kind of fell apart. And then in about 2005, 2006, Geoff Hinton resurrected an algorithm that we'll talk about a little bit later, which was the restricted Boltzmann machine algorithm, and showed that a multi-layer version of the restricted Boltzmann machine could do surprisingly interesting things using binary nodes. So this then led to, and he coined the term deep learning. And while working at the Gatsby Center in London with several people there, developed these algorithms further. It was basically, it turned out that although the restricted Boltzmann machine learning algorithm had some very good, strong foundations in statistics and statistical thermodynamics, that in fact it was faster and easier to train these things just using backpropagation. That then led to the current resurrection of backpropagation in essentially the identical form to what existed in the 1980s, with the difference that the computers are somewhat bigger and faster, and the data sets are much bigger. So back in the 1980s, when this was being developed, your typical hard drive was between 10 and 20 megabytes. The internet would run at sort of dial-up modem speeds, somewhere around 56,000 bits per second. And so large data simply wasn't really an option for testing many of these algorithms, and also parallel processing was just in its infancy. So now with the larger networks, this has been resurrected. But and I will go, and this chapter goes through a lot of the thinking about this, but I wanted to put this in context because the algorithm still has a lot of the weaknesses that were discovered and extensively studied in the 1980s and 90s, which is that it's a model that can approximate many things without giving you any insight into them, and that remains a problem for this. That doesn't mean that it can't give you insight. It just means that there's nothing about this model. It's such a powerful approximator that you can apply it to many types of problems in ways where it functions just like a black box. This is one of the reasons in this course I really don't want you using sort of black box software, because I think that makes people fall into these habits. I think that this algorithm, backpropagation used properly and understood properly, can in fact be a very powerful tool, but you do need to understand exactly what it's doing and why it's doing it. So let me take you through this. The development in Haken is not that different from what I'm going to show. I'm just going to do I just did the math a little bit differently because it makes it easier for me to remember it, in what might be a little bit more of a vector fashion. The downside of doing this in vector fashion, as you'll see, is that some of the transposes make it a little bit hard to get all the details right. So the overall structure of this kind of network that we're going to look at is that we have some kind of an input layer. Oops, sorry about that. Let me get this my drawing to work here. I've got an input layer, which we will call X, and these are now all vectors. So X has a bunch of nodes here, and it goes through some, and then there's some kind of linear output here, Y, which may or may not have the same size as X, and there's a matrix W, which connects X to Y, right? So now Y equals W transpose X. And in this case, W should be seen as a matrix, right? In previous chapters, W, we were just looking at a single output, so W was just a vector. To maintain consistency, I'm going to put the transpose in. Actually, I'm sorry. Let's see how we're going to do this. I'll do my best to maintain consistency. One could use the transpose there. In fact, it's pretty typical in the literature that people wouldn't. They would just put a WX like that. I'll do my best. I don't think I've got it right in all cases. So this, let's leave the transpose in there for now. So now what happens, you have X goes to Y, and now you have a nonlinearity here, which is sort of this sigma nonlinearity, which might or might not be a sigmoid. So that nonlinearity, it could be that, sigma of Y could look like that. Right? And now we do it again. And now here, the outputs of these are these little nodes, and each one of these is just a straight flow through, right? So that each element of Y is a vector, but each element just flows through a single sigma and gives a single output. And note the difference between that and this matrix, right? The matrix here has the ability to sort of mix all the X's together to produce these outputs, but the sigmas don't. It just, they operate on a single layer, on the single value, scalar values. And then that goes through another weight matrix. There would be some outputs here, and that goes through another weight matrix up there. So now to maintain the labeling on this, I'm going to call this this bottom layer maybe X1, W1, and Y1. And then this thing here becomes X2. These things here are X2, right? Once I've gone through this layer, that's X2. This thing becomes W2, and that thing becomes Y2. So that in general, what we'll write the equations will look like this: Yn equals Wnxn is just the linear component. It's each X running through the weights to generate the linear output Y. And then Xn plus 1 is running that sigma through Yn, where sigma here is understood as a function that again is this sort of one-to-one. It takes each element of Y and applies a nonlinearity to that element of Y. And it could be written like this as well. And then at the output, you have some kind of error, because there's something you wanted to do. You basically have the function you want is Y star equals some function of X1, right? Because you're going to put something in at the beginning of this, and you're going to have some Y star. But what you're actually going to get is you're going to get Yn is equal to your network. So we'll just call it the network, which is going to be a function of all of X1 and all of the W1 to Wn's, right? So that's going to give you your Y. And so your error is the difference between what you wanted and what you got at the top level. Because this thing, of course, can have many levels, right? You could keep going. I could put more sigmas at the top of this, and then I could put more W's and more Y's, and you could keep going for some number of layers, right? And then the cost function, and we call this delta, and maybe that's just the delta n, right? Because that's sort of the error at the top layer, at the nth, the top layer of this thing. And the cost function is at the output, right? It's in this case, if we write that as a column vector, delta n transpose delta n is sort of like, that's the vector equivalent of the error squared, right? And so the expected value of the squared error, and we put the half in there just because it makes the math work out better later. It doesn't really matter. So these are so this is the overall structure of a multi-layer perceptron, or a multi-layer network, or a deep network, or however you want to call these things. And that's exactly what Haken has in his book. So we have here the way I've labeled it. This would be X1. This is W1. That's now here. This is Y1, and then X2, right? Which is there's some kind of sigmoid nonlinearity there. This becomes Y2, X3. This thing might be W2. This is W3, and this is Y3 in this case. Right, which is the output signal. And the things that you're trying to do is you're trying to get from this to that. Everything else is considered hidden units, under the idea that if this were a brain, this might be your eyes coming in, and this might be your arm doing something, reaching to something, and in the middle is what the rest of your brain is doing. And that really is reflected by the fact that you don't necessarily know, these middle units don't necessarily have any meaning, right? These could be pixels of an image, these could be signals to muscles. So those have some meaning in the outside world, but the stuff in the middle is just intermediate steps in a computation, which may itself not have any real meaning. So that's the overall structure of these networks. We often refer to them as LNL computational structures. It's an older term, but it will show up in other domains: linear, nonlinear, linear. And the important point is it's linearity alternating with what might be called a static nonlinearity. And again, that's this point where the W's here have this sort of mixing and the sigmas do not have a mixing. If these represented time points, right? If these were lagged time points, the x from samples from an input signal, then you imagine that W here is like a filter on those lagged time points, right? It's a finite impulse response filter, which is producing outputs in Y, whereas the sigmas are memoryless transformations, right? They take the current value of a measurement of a voltage and they produce a different voltage from that, but it doesn't depend on past values. So that's where this terminology comes from, the idea of a static nonlinearity. It's static in the sense that it's memoryless. If this was a vector of lagged time samples, which it might be in some applications. Okay, so the proof of backpropagation, which is here, which just looks like a whole lot of math, but I'm going to take you through it because I want you to understand this. So you start out, as we always do, with some cost function. And remember, what we want to do is we want to get to the point of saying our learning rule, delta W, is going to be the gradient, is going to be the negative of the gradient, right? We want that to be the negative of the cost function with respect to W. Because we know that if we do that, then we have dj dt is equal to dj dw dw dt, and then this will be guaranteed to be less than or equal to 0, right? Because this is dw dt. Right, so if we take that and plug that in for dw dt, and this thing, and that's equal to negative dj dw, we know that the product of those things is less than 0. So that's where we want to go. So the key, of course, is to calculate this term dj dw. And now remember, it's a multi-layer network, so the W's, that we've got different W's at each layer. So the first thing we can do is to figure this out is we can start at the output layer. So a lot of this stuff is going to look very familiar from the LMS rule, because it's all based on that. So here we're going to start now at the output layer. So here we do DJ, we say DJ DW. We also use the chain rule to break that into DJ with respect to d delta n. Remember, delta n is the top layer, the last layer error, right? That's the error at the output of the network. Okay? So dj dw is dj with respect to delta n, the output error, times the partial of the output error with respect to the weight. And that's pretty straightforward, right? Because it's very easy, if this is where we put the 1/2 in. If we look at dj d delta n, we're just going to get, it's just equal to delta n, right? Right. So we got that, that's that delta n term comes out. And d delta n, dwn, is just, so delta n itself is y star minus y, yn, and yn, so that's equal to y star minus wxn, right? So if I, in fact, let me, you could do this either way. I just keep the negative terms. Let's keep the negative terms. We're going to call this yn minus y. And then so if we, so that's, and so if we look at this derivative, that gives you, it just becomes wxn. Okay. So, I'm sorry, it just becomes w. Apologize, because you're taking with the derivative of delta, right? So what happens here is you have yn equals w n xn. So if we take the derivative of delta n with respect to wn, we get just xn out of it, and that term shows up here, right? So, and this is LMS. That is the LMS rule. So that, and because remember, what does LMS look like? It looks like y star minus y times x, right? And so if we wanted to set, and again, what we would set is you say delta W is equal to the negative of gamma times that thing, times this. and that gives you LMS, right? So so we expect that, right? Because at the end, at the top layer of this, if you just look at the top layer here, that's just a linear network. And if we were to do gradient descent on a linear network, we're just going to get LMS. We know that LMS is gradient descent on a linear network where for a quadratic cost function. Okay, so good. So we found that. But now here's the more interesting thing. What happens when we look at the cost with respect to the next layer down? This is the tricky thing. How do we tune these weights? Right? Okay, well, let's just figure it out with the chain rule. So in this case, you get the same, use the same trick. You have the cost dj with respect to the top level error with respect to the next layer down. And now we go back, dxn dyn minus 1. What I mean by y, remember it's here, here's xn, here's y of n minus 1. Right, so this is taking me back through the nonlinearity. Yeah. And now I have to do dyn minus 1 with respect to dw. Now, again, watch the trick here. In the middle, I'm only looking at these xn's. I don't look at, nowhere in the, you could do the chain rule lots of different ways, but you don't want an intermediate, you don't want to look at dj, dwn anywhere in the middle of this. And you could say, well, seems like I should have looked at that, right? Doesn't the top layer weight matter for this? Well, it does, but those top layer weights, the point is we're going to assume in this process that when we try to calculate how we're going to change this layer, that this layer is not changing at exactly the same time, right? That there's sort of a, that each layer is going to be modified, assuming the other ones are fixed. And that's true, because anytime you actually do this, you're going to have to do this on a sequential computer, and these things aren't going to happen one at a time. Okay, so now we have this equation here, and so now I have those terms. So let's figure out what those terms are. We already know what the first term is because we already figured it out from there. So that gives you your delta n, right? D of delta with respect to xn. Well, we know, for instance, that again, delta n equals y star minus y n. And yn is equal to wn xn. So if we take the derivative of this thing with respect to that, we just get this. There's some minus signs in there, and trust me, they all cancel out the right way. The d delta n with respect to dxn here gives you this term, gives you that wn, right? So you just get that wn. So we're checking. So we basically checked off the first one. We've checked off the second one. Now it's the third one, dxn with respect to yn minus 1. Well, that's the static nonlinearity. We're just going through sigma, right? So that is so d, if you just look at one of them, dx dy is remember x in this case, xn equals sigma of yn minus 1. So it's just, so this derivative is equal to sigma prime yn minus 1 times yn minus 1 prime, right? Essentially, well, in this case, I don't need to put that second term in there. It's just this sigma prime of yn minus 1, right? It's just the derivative of sigma evaluated at that point, okay? So that's what we put in here. So now at this point, we put in, and I'm using this terminology here to make that clear, but this is the derivative of sigma evaluated at the point yn minus 1. Right? Okay, so now I've got that term. And now let's look at the last one, derivative yn minus 1 with respect to the weights. So remember, in the middle, all the middle terms, I'm using only the x's occur. And the last step, I finally take the derivative with respect to the thing I care about, which is the weights. So dyn is just xn minus 1, right? Because yn minus 1 equals wn minus 1 times xn minus 1. No? So that comes out, right? So now I've got all my terms, and I get that. And now what I'm going to do is I'm just going to label, I'm going to call this entire thing delta n minus 1. I'm just going to define it to be delta n minus 1. Because now this has exactly the same form as the LMS rule, right? Now, it's just a labeling, that delta n minus, I just called it that, right? but but that's fine. And we'll see why I did that. So now let's go on to the next level. So now I'm going to go one level down, right? This is the top, that's one level down. Now let's go 2 levels down. Okay. So again, I have up at the top, this is yn, this is xn, the weights between here are wn. I have my sigmas. Then I have here yn minus 1, xn minus 1. I've got something here, wn minus 1. Still got some sigmas. And I go down one more. Let's make some space here. Down to xn minus 2. Well, so the same thing. So I'm just going down one more level. And again, I write the whole thing out. Again, look at the pattern here. The top level, so that the cost with respect to the output error with respect to the x one level down, x with respect to y with respect to x with respect to y with respect to w at the last step. Okay, so same pattern. And that is just, again, just a chain rule of differentiation. And I can write these things out, and then so here I've got this becomes that, just like we had at the top level. This becomes my sigmoid. And now dy n minus 1 dx n minus 1 gives me this. Now I get another sigmoid here, which gives me that. And dy n minus 2 dw n minus 2 gives me the x of n minus 2. Right? So now I have this equation, which looks a lot like this one. And in fact, if I, you notice that up here, I define delta n minus 1 to be this thing. So that delta n minus 1 term is right here, right? So that's, I already have this delta n minus 1 term right there. So I'm going to write that, I'm going to encapsulate that. And then I have these terms here, which show up here. And now maybe I'm going to call this whole thing delta n minus 2. Because then I get, again, back to the same form of the LMS rule. Yeah. So this is where the recursion comes from. So now you get the sense that I can define these delta n minus 1, delta n minus 2, I can define in a recursive fashion. So that at any level, the delta n minus 1 as a function of the delta above it looks like this. And now in here, I've had abuses of notation, and if you try to write out the transposes, it's not quite going to work. I did it in this way so that you could see the pattern. What actually happens is W is a matrix. It's W. So if Y equals WX, then it's, if you're going to multiply delta lives in the Y space, right? Remember, delta looks like Y star minus Y, right? So delta and Y may not be the same size as X in any of these things, right? So that because delta's in the Y space and Y equals WX, you have to use the transpose here, or your, MATLAB will give you a matrix multiply error, dimensionality error of some kind. But in fact, the transpose is the right answer. The reason it's, again, remember, this came from the derivative. It's not the inverse, it's the transpose, right? So, and then here, what's this term diag? Well, what's actually happening is I'm just trying to reflect the fact that this is a static nonlinearity, right? It's, so sigma prime of Y, of each of the elements of sigma prime. Let's do this. You've got sigma prime is a vector, right? So sigma prime looks like this column vector. I can't multiply a column vector times this thing, right? That thing is also a column vector. What I'm really doing is I want to multiply this times that, the next element times that. I want to do these pairwise multiplications. In MATLAB, it's the dot star operator, right? So what does that really, if you were to write this out mathematically, what does it really look like? Is what you do instead of that operation is you just take sigma and you put it on the diagonal of a matrix that looks like 0, right? And now when I multiply by this vector, the first one multiplies times the first, second times the second, and so on, and you'll get what you want out of it. So if you wanted to write this out, technically you'd use this diag operator, same as the MATLAB diag operator, to take this vector and turn it into a diagonal matrix, right? Well, the reason I like to write it out this way is I just like using the vector notation. You don't end up with all the crazy subscripts. If you most derivations that you'll find where people derive this, and including Haken, they just write it out with the subscripts, and you don't have to worry about whether it's a diagonal matrix or not. It just works out. Okay. But so the point is, what you've got in this structure is you have a recursive algorithm for the deltas, right? Delta n minus 1 as a function of delta n. You also have a recursive algorithm for the x's, right? So xn plus 1 is here is a function of xn. So you've got a forward recursive algorithm, which gives you the forward pass through the network, and you've got a backward recursive algorithm, which gives you the backward pass through the network. So get this up here. This is your backward one, right? And it's called back propagation because you back propagate the errors. Now notice that unlike the forward version of the algorithm, the back propagation does depend on this thing from the forward propagation. They're not independent of each other. You have to do the forward propagation first, right? First of all, you have to do it first because you don't know the error at the output until you generate the output. So you have to run through, calculate the output of the network, get this top y, calculate that top n, which is what you want minus what you got, and then you backward propagate it. But you have to save all these yns along the way because you will need them to figure out where you are on the derivative. Yeah. And then once you've done that, you do your forward propagation, you do your back propagation. Now you have the values of the data. You've got x at every single level and y at every single level, including the output. And now you've back propagated, so you've got the deltas at every single level. Now finally you're ready to learn just the way you normally would have, right? So now you set delta wn equals negative delta nxn, because at every level it is true that this is equal to the negative of the derivative of the cost with respect to wn for that level. And you do this for all the levels at the same time. And that gives you your update, okay? So it's quite clever. And the reason it's clever is because of this recursion, because you get this recurring pattern that allows you to do that. Now, there are similarities. This is not identical. But you can make the similarities of this. To those of you who are familiar with sort of optimization, time-based optimization problems like Bellman problems or the linear quadratic regulator, things like that, these are very similar. So, for instance, you're generally aware that there's a forward propagation of state and a backward propagation of error. And this is very closely related to that idea for very similar reasons. The difference, however, is when you're doing the forward propagation of state and the backward propagation of error. Typically, so for instance, you might have a forward propagation of state. Stop that. So suppose you have a linear system, x dot plus bu, right? I'm going to propagate state x forward in time, and then until I get to some, x at t final. Let's write that way, x at t final. And then I'm going to calculate some error, which might be in the term, might look like some form of quadratic error, perhaps of the same form. It could be, in those cases, it would be something like xq, x star or something. Which I'm then going to propagate backward as errors using the Riccati equation. And the Riccati equation will propagate this thing backward, right? So it feels very similar. And in fact, these are similar for a very, very precise mathematical reasons. The difference, however, is that in this case, your goal is to find u of t that drives x to where it wants to go, right? That's the standard control theory. So in control theory, or in optimal control, what you're trying to do is find u of t. In neural network learning, what you're trying to find is essentially a of, in this case, n, right? We're propagating up through the layers of this rather than U of t. So the algorithms that are used to do the optimization are different, but the outcome goal is essentially the same. And they're very close relations. People who know the Pontryagin minimum principle and the ways in which these things can be solved using sort of Hamiltonian mechanics, it's very closely related. If I can find a paper on that, I'll upload it for you guys. But it's worth realizing that there's many of these things reinvent the wheel in different forms. The reason it's important to know that is that as there are efficient algorithms, there's sometimes efficient algorithms from other fields that'll be important. You will see there's a lot of situations where these forward-backward algorithms, another very important forward-backward algorithm is called the Viterbi algorithm, which is used for hidden Markov models and was the basis of CDMA cell phone encoding, which is no longer used, but it involved a very similar sort of fitting process. And the reason this is sort of a fitting process is because what you're trying to do is you're trying to fit the optimal weights to this propagation of a particular data set. So the data set has inputs propagate forward and statistical outputs which propagate backward. And you want these all to line up in some sense that minimizes some kind of error. And ultimately, you're going to be minimizing the error at each level. Okay, that's a lot of hand waving for that, but I just wanted you guys to be aware of these things. Okay. I don't know if you guys have questions at this point. Let me see. There's some. I'm seeing a couple things in the chat here. Let me see if I can. Okay. The questions that had come up were primarily about what the cost function is itself, and it sounds like this may have been answered, but let me just make sure that that's clear to everybody. What you're always trying to do, again, our goal is that we have some sets of pairs, X and Y. We have values of X, let me call it X of time, and Y star of time, or something, so that we just have lots of different values of these. These are pairs. Right? And what I want is I want to find an approximate function, Y hat, looks like some function of X, right? Or more importantly, Y hat at each point in time is approximately equal to F of X at that point in time. The reason I'm using T as a marker here is I'm using the subscripts N to indicate where I am, which layer I am in the network, and I'm trying not to confuse that. So, but these are the inputs and outputs. So technically, this Y hat is YN, the output of the network, and this is X1. Right? So what's at the input and output of the network? Or again, if I'm thinking of a multi-layer network, I've got some multi-layer number. I'm putting some. I have a set of X's that go in. I've got a set of Y's that come out, and each X is supposed to be related to some Y by some function. So there's some true function, and then I'm going to approximate this function. So for instance, maybe there's a true function here, such that Y equals F of X, and then I'm going to approximate this as the output of my network, YN, is equal to some network function of F of X and W. And I want these things, I'm calling this Y star, to be the correct answer. And so I want to say how I want these things to be. So for any given X, I'm going to look at the difference between Y star and Y. Right? So these could both be thought of as functions of X. So it's actually Y star of X minus Y of X. And I'm going to, for all of the X's, maybe I take the sum of over X of that difference, and I could square it, or I could take its absolute value, or I could do a number of things, right? Pretty much any, if it's absolute value, any power of the absolute value is a valid way of doing this. There's lots of different ways in which you could set the cost function. But what this is basically saying, and sometimes we'll write as the expected value of Y star minus Y, remembering that these things are random variables. So that's the expected. It's the standard deviation, right? It's the mean. This is the mean squared error, right? So that's the mean squared error. And so what's the average squared error? And we're going to call that the cost function, and we want to minimize the cost function. So we would like to minimize that cost over all possible functions over all sets of W. That defines the set of functions here. So that's the overall idea here, right? And that's where these cost functions come from. This is by no means the only cost function. It is the only cost function that leads to the backpropagation algorithm. So if you use different cost functions, you won't get that. For instance, there are different classes of cost functions that can be used in other contexts. If your goal in mean squared error, so a mean squared error cost function is something like saying, I just want to, let me think of a control thing. I've got a line I want to follow, and I'm going along that line. I just want to stay close to that line. Occasionally I may go off the line, but on average, I want to be close to that line. Okay, that would be sort of a mean squared error kind of problem, right? But suppose that line were actually a road, and on this side of the road is a cliff, and maybe on that side of the road there's a cliff, and I really don't want to go over those cliffs. Now, mean squared error isn't very good because mean squared error tends to give you Gaussian distributions across here. I don't want a Gaussian distribution across there because that gives me some finite probability I'm going to fall off the edge. So what I really want is to make sure I never go over the edge. So now so in this case where this cost function, maybe I want to minimize y star minus y squared, expected value of that. In this case, I may want to minimize the maximum value of y star minus y. Right? I might want to say, never let it go beyond this, beyond the absolute maximum. I care what that maximum is, or I just want to find it. I mean, there's a cost function, or it may be that I absolutely require this, that has to be less than some value v or something, right? And that will say I have to stay on the road, right? That's the maximum deviation. I can be anywhere in here, but I can't go off the road at any point. Other situations where this kind of thing would be relevant is if you're looking at a stock price, and your stock price is here, and you're trying to control it in some way. Negative doesn't exist, right? You're bankrupt here, right? It can go up as high as you like, it can move around, but as soon as it crosses zero, you're bankrupt. Bank shuts you down. So that there are lots of cliff-like phenomena where the mean squared error is not the correct error metric, right? Because it doesn't really represent the actual cost, right? It's a cost function. It's just mathematics, which is trying to represent what the cost should be. There are, common errors that are used, or common metrics, is what we call the L2 norm, which in this case is the expected value of delta squared. You have the L1 norm, which is the expected value of the absolute value of delta, which could be considered, if you want, you could write that absolute value to the 1, absolute value to the 2. And then you have what's called the L infinity norm, which is essentially the max value of absolute delta. Okay. So those are typical. These are all valid cost functions, and those are very typical ones that could be used. If you want to think about this in a different way, let's suppose you look at what these norms look like for when delta is say two-dimensional. So here's delta 1, delta 2. The L2 norm looks at the expected value of the square, right? So that is going to basically the constant surface values of that are going to look like circles, right? So this is constant value L2 norm equals constant on a circle, right? The L1 norm is constant here. This is basically because this is the sum of all those terms, right? I'm just adding up all the deltas, literally, right? Because it's if delta is positive, the expected value of this is I'm just adding them. So it's going to look like this. again, because this thing looks a lot like the sum over the examples of delta squared. This looks like the sum over the examples of absolute value of delta, and this is the max of delta. And the max one looks a lot like this. These are the equal value things, and there's sort of delta functions around these things, right? Wherever you are, right? Because no matter where I am, I'm just gonna sort of immediately snap to whatever the maximum value is in some sense. And you can imagine that there's lots of things in between. You know, what's the L3 norm and the L4 norm, and they're all going to have a variety of different different shapes in these things, right? So. Actually, I'm sorry, it doesn't look like that. The L infinity norm looks like, I'm writing it as a different form. It looks like a square. It's the L infinity norm. So that's the L2. This is the L1. And the L infinity looks like a square. Wherever you are, you sort of snap to the nearest nearest value that you're larger than, right? So for instance, if delta 1 is greater than delta 2 in this region, I snap out there, right? So it looks like that. And you can imagine that all of these other ones look like things that are sort of in this zone in some way. Right? So these are a bunch of different norms. For the most part, only L1, L2, and L infinity ever get used in anything you're ever going to see. Right? So those are different kinds of cost functions. Again, for LMS, least mean squared, the name tells you the norm that they're using, and that's important. And backpropagation implicitly uses this mean squared norm, because it doesn't work otherwise. The reason that the L2 norm is related to Gaussians is if you look at over all functions, let's say, trying to think how to, well, I mean, the Gaussian essentially has the smallest L2 norm over all bounded functions on its range. We don't have to prove that here, but the Gaussian is related. Things with L2 norm tend to work well when the statistics are Gaussian, and we may come back to that at other points. Does that? Other questions? Does that that may be more than you wanted in your answer, but hopefully that gives a sense of where the stuff is coming from. Okay. Let me keep going here. A lot to cover, not all of which we'll cover today. Obviously, backpropagation allows you to do all sorts of important things, right? It allows you to suddenly solve things using these separating hyperplanes. Well, separating hypersurfaces. It allows you to create surfaces. Particularly for the example that the book gave, it does a pretty good job of finding this. Remembering that before, you couldn't do anything other than straight line separators. So this gives you obviously a lot more capability. Haken spends a lot of time looking at variable learning rates. Remember, I said learning rates are almost always set to be small constants. But you can use the Hessian to set learning rates the same way that we talked about with LMS, and the derivations he gives are pretty much the same. If the curvature, and this is the curvature of J of W with respect to W, is low, then you can move very fast. But if the curvature is very high with respect to W, then you don't want to move so fast, because if you do, you'll just overshoot. Okay. So in other words, the lower the curvature, the faster you can do. So you can set gamma look like 1 over the Hessian in some way, or like Hessian inverse. You can set it to look like the Hessian. So you'll see that in a lot of places. This comes back when we look at the optimal brain damage or optimal brain surgery thing. The criteria for stable convergence, let's see if he put them in here, I believe, are the, see where it went. I lost it in here, sorry. The criteria for the stable convergence you've seen before. These are the Lyon criteria. Remember that we need, the sum goes to infinity, right? So that there's enough power, there's enough energy in the learning rate that you never stop learning. and you need the, it's not that you need the sums, you need it to be bounded. It's actually, he got this backward. It's the sum squared has to be less than infinity. But the Lyoung criteria, remember, are that the, so typically if you set gamma equals 1 over time, then you're going to have the sum of gamma equals infinity, and the sum of gamma squared is bounded, right? And that's important. That's important for these criteria, that it converges fast enough, but not so fast that you that you stop early because your learning rates drop to 0. And again, remember these things. Now, if you look at these in terms of gamma, sum of gamma, particularly if you put the absolute value there, is the L1 norm. Sum of gamma 2 is the L2 norm. So we just talked about norms. Those enter in lots of different places. Okay. The we've talked about overfitting, and this happens, and he talks about it again here, which is that, again, we're learning these are very powerful algorithms so that they have the ability to learn, to fit lots of different functions. This function, even though it's very wiggly, fits your data points, your training set, just as good as this function, right? And this points out that this has very low constraint on the fitted function f of x w, right? In other words, I can fit lots of things. It's a very powerful network. This has high constraint. In other words, a less powerful network on f of x w. And what that means is the less powerful network, in the sense that it can only do smooth functions, did a better job of approximating these points. Well, maybe it's a better job. I don't know what's a better job. You don't know what the right answer is, right? I mean, suppose that now, okay, I've just trained this and now a point comes in over here. This one's going to fail and this one might be dead on, right? So you don't know what the right answer is, but usually there's an assumption. So what you're trying to do is you want to say f of xw is the set of functions that you can approximate, right? Your network model specifies the set of functions you can approximate. And you want that set of functions to be the right set of functions in some sense. It could be the right set of functions in the sense that they are the only feasible functions, right? If I'm trying to approximate the position of a moving object. Moving objects don't suddenly jump from one place to another, right? They will move smoothly following Newtonian mechanics. So I know there that I only need to represent smooth functions. If my network represents non-smooth functions, it will be able to approximate, but its interpolation won't be very good. Its prediction won't be very good because it can approximate things that aren't possible in reality. So I want the set of functions to be limited to the class of functions that I know are possible. That's one reason you might limit it. Another reason you might limit it might be because you want it to have some behavior. So suppose now I'm making a self-driving car. Now I want this thing to drive smoothly. I don't want it to be hitting the brakes all the time. I don't want to be swerving in and out of lanes. In that case, I might also constrain the network to generate only smooth functions, not because that's a reflection of reality, because that's the class of functions that I want to get, right? So, and there may be situations in which I really don't know. Like I'm trying to think, what are the class of functions that allow me to recognize human faces? I don't know if those are smooth or not smooth. And so now I'm in a lot of trouble. And so now I just have to try it a lot and see how well I do. But again, the choice of the class of functions that you're going to approximate over is very important. Networks are very tricky because it's very hard to specify the class of functions. A multi-layer perceptron, a multi-layer network, generally does approximate continuously differentiable functions, but they don't have to have very strong smoothness properties. If you don't let the weights be bounded, you can have arbitrarily sharp transitions, right? If I have a sigmoid, come on, sorry, losing my pencil here. If I have a sigmoid function like this, right, so that y equals sigma of x, okay, fine, that was good. But suppose I put y equals sigma times very big number k times x, right? So that's now going to give me something that's going to go very steep. And if I let k get very big, this thing becomes like that, right? It's going to become almost a step function. So that if I allow unbounded weights here, k is on the weights, right? If I allow unbounded weights, I can get things that, while differentiable, have arbitrary sharpness to them, and maybe I don't want that. So if I really want things that are smooth, I need to put additional criteria on the network. Okay. This brings us to the universal approximation theorem. A set of functions. So there's this concept, dense. This is a mathematical concept. A set of functions is dense in a function space if for every function in every function you could find that function space, and I can pick a small value of epsilon. There's some parameters such that my set of functions are within epsilon. In other words, suppose I did this in a set of points. I say I've got a bunch of points here. And I say, okay, I'm now going to pick another point here, and where I can pick any point anywhere I want. And I want to say, how far are these 2 points? Is this from the nearest point that I have, right? And I want to say that I want that always to be less than epsilon. Right, always to be less than epsilon, no matter where it is. So if the black dots are dense in the set of all possible red dots, then I can always find a black dot that's close to a red dot. So one example of that might be the rational numbers are dense in the real numbers. So for any real number and any finite epsilon, you hand me an epsilon, 10 to the negative 200. So it might make epsilon very small. I don't care, right? And you say, you know, and you hand me that epsilon, and you hand me some real number, some value q. I can find a rational number. Well, you know what, I'm gonna, you'll say you hand me some real number, call it x. You have me a real number x. I can find a rational number q such that x minus q is less than epsilon. Right? You're not allowed to change this once you choose it. Right? You choose an epsilon, but you can hand me any real number you want. I can always find a rational number that is within epsilon of it. Right? Obviously, they're not equal, but within that. So the rational numbers are dense in the real numbers, which is surprising, right? Because you know that the rational numbers are countable and the real numbers are uncountable. There's a lot more real numbers than rational numbers. A lot, you know, not just an infinitely infinite number more real numbers, and yet they're dense in that. So you can have the same concept for functions. So let's look at you know, here's an example, the Taylor series. So the set of functions that can be written as f of x equals you know, a plus b x plus cx squared plus dx cubed, right? So the Taylor series, or what we call a set of analytic functions, is dense in the space of continuously differentiable functions, which is good for any finite Taylor series, right? So the other way to think about that is that the set of functions with finite Taylor series is dense in the set of functions with infinite Taylor series, right? Because I can take any function of x. I can always write a Taylor expansion, right? And I can, in this case, I can write that Taylor expansion going out to infinity. And then I can take an approximation Fn where I just have the Taylor expansion from 1 to n of, you know, a I x to the I. And that's not equal to the situation where there's an infinite number of these, right? But I can always find, if you give me epsilon, I can always find an n such that f minus fn is less than epsilon, right? So for all epsilon, there exists an n such that f minus fn is less than epsilon. So the set of finite expansion Taylor series is dense in the set of all analytic functions. Okay? Does this make sense so far? Stop me, put something in the chat, speak out if this doesn't make sense. This is important because what you're talking about now in a neural network is, remember, a finite expansion Taylor series only has n of these parameters, right? The parameters, the weights of the Taylor series are the coefficients in this polynomial. But a finitely terminating Taylor series has just a finite number of these weights. And I'm saying that I can get arbitrarily close to any function I want using a finite number of weights. That's important for a neural network. I don't want an infinite sized neural network, right? So what you basically say is the equivalent for a neural network would be the finite sized neural networks are dense in the set of all smooth functions, which is basically what the universal approximation theorem shows. That's not a proof, that's just the definition. You still have to show not all function sets are dense, right? For instance, if I said, what about the set of Taylor series where all the odd coefficients were 0? Well, that's obviously not dense in things, right? That's only dense in the set of symmetric differentiable functions, things that are symmetric about 0, right? So the problem is, not all things are dense and all other things, right? There's lots of examples of things that don't work. But for sigmoid nonlinearities in a multi-layer network of the form that yn is equal to sigma of wn xn. Sorry, let me write it the way I did before. Xn plus 1 equals sigma wn xn for the set of networks. And in fact, this is true, I believe, just for 2-layer networks. And actually it may even be true for single-layer networks. And this may be true just for single-layer networks. So if you have an output, a network of the form y equals w2 times sigma w1 x1, I believe this set of functions is dense in the set of all differentiable functions. But you may need a lot of them, right? You may need the number, the dimensionality. I mean, x has a fixed dimensionality, y has a fixed dimensionality there, but this x2 may be very, very big. Could be very, 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 very big, right? That the structure of this network, as I'm drawing it now, looks like this. I might have, well, actually, let's just even do it as a one-dimensional network. Suppose just x is just a scalar, and suppose my desired output y2 is just a scalar. And in here I've got, that's y1, that's w1. Then I've got here's the sigmas. I do little sigmas there, so that becomes x2. And this thing becomes w2, right? So that's the structure of this network, right? It could just have a scalar input and a scalar output. But to approximate arbitrary analytic functions, I might need a very, very, very large number of hidden units. The proof of this is not all that hard, actually, but it constructs very stupid networks. What you can do is, if I have a sigmoid that does that, I can make this thing arbitrarily sharp. How strange, just trying to correct what I'm doing here. I can make this thing very sharp by using a very high value kx, right? So sigma of kx, if k gets large, this gets steeper and steeper. I can also construct sigma of negative kx, which would do the same thing in this direction. I can put an offset in here, as we did before, plus little b's, so I can put this thing arbitrarily close to that thing, right? And then I can I can add them up in the middle or subtract them or something, which allows me to calculate these things. So now I can make little bumps out of these things, right? So now I can make lots of little bumps, and I can add lots of little bumps together to make a function that approximates smooth functions like this. That's not a very clever way to do this, but all I need is the existence proof, right? So these universal approximation theorems are not as helpful as you'd like, but what it does say is be careful. These are universal approximators. so that if you make a big enough network, you can overfit anything. So you have to be careful about that. You don't, in general, you do not want very large networks because they will overfit. When you look at the errors, there are two causes of errors. One is underfitting, right? So you could have a poor model in the sense that you're trying to approximate a smooth function by a non-smooth function or vice versa. You can also have a poor fit to the models that you've got, or a poor choice because the learning algorithm itself might not converge. So those are other sorts, that's the error going the other direction, right? You can have the error where I overfit, but you can also have the error where I underfit, right? I'm trying to, I've got a bunch of points that look like this, and my model is only linear. So I can't do the rest of these, right? Or the points are sinusoidal, and I've only got 2 or 3 hidden units, so maybe I can approximate this, but I can't approximate the rest of them. Okay. There's this concept of the curse of dimensionality, which isn't as bad as it sounds, but it has to do with the fact that if you, it's hard to approximate things in very high dimensional spaces. If I have a bunch of points X and I take some samples here in 1-dimensional space, I might be able to fit a function to that. I've got 4 samples in a 2-dimensional space. If I'm in a 2-dimensional space, X1, X2, and I can take 4 samples and I'm trying to get a surface out of that, okay, maybe. If I have a 3-dimensional space and I've only got 4 points, it's much harder to know what it was the original function was. Now imagine I've got a 300-dimensional space, right? So in these very high dimensional spaces, there are many more functions than you're going to have data. So you don't constrain the set of functions very much. That's essentially what the curse of dimensionality is. The higher the dimensionality, the more data you need in order to be able to figure out the set of functions, because there's a lot more functions on high dimensional spaces. Okay. And we will see that more and more throughout the course. I'm not going to have time to talk about all the weight decay algorithms. He does a reasonable job looking at that. Basically, it's the same concept I was talking about before. If you have a network which has a valley in it. So this is the cost function, J of W, and maybe these are the 2 directions, right? That's W1 and W2 for 2 different components of the weights. This is supposed to look like a valley in some sense. And I want to know, could I get rid of one of these weights in some way? Well, if I were to delete one of them, the actual value of W1 doesn't matter very much, right? Because I don't change, my cost doesn't change very much as I move in W1. But the value of W2 matters a lot because I might go up and down this. So, so the point is that if I were to delete one of these, I could delete W1. And that's basically what happens. So you can delete things that are very shallow in the valleys, because once everybody else is converged, you're pretty close to the minimum, even if I got rid of that. So what happens is that you delete that, you still have to retrain, because the way they're incorporated into the network is complicated. If you just delete something, set it to 0, that may mess up the whole thing. So you still have to retrain, but you've basically found that weight wasn't so important. You could get rid of it. Actually getting rid of it is an extreme. Really, the right answer for this thing would be to quantize it differently. So you might have W2 might be 16 bits and W1 might be 8 bits. That would be a better way to do this, right? You quantize relative to the Hessian. Actually, it would be sort of the log of the magnitude of the inverse Hessian. But generally, that would be one way of doing this. The other thing that people do is basically what the Newton algorithm does is you normalize everything by the inverse Hessian. So you basically, you can take that inverse Hessian, you can multiply that in some way times the weights. And now what happens is that this all just becomes circular. So you don't have this problem. And now you can quantize all the transformed weights the same amount. But basically it's, in the extreme, if this were completely flat, then the weight in that direction doesn't matter at all. The inverse Hessian won't even exist. And so you can safely delete that weight with having no effect, right? That weight essentially has no effect on your cost. That would be like saying, suppose that I have a function y equals f of x1 comma x2, where y is just equal to x1 is the answer, right? So now if I build a function y hat equals w times x, which is equal, say, w1 x1 plus w2 x2, I can just safely delete this, right? It doesn't matter. So no matter what its value is, I could get rid of it. Okay. That's the idea of this optimal brain surgeon, or what Jan LeCun's original term for it was, optimal brain damage. Where you sort of, you can delete if you had to delete weights, which ones would you delete? And it's called weight pruning. Interestingly, pruning is a feature of biological systems as well during development. The last thing I want to talk about here is this issue of these bottleneck networks, and we'll talk about these more when we get to unsupervised learning. But suppose I try to learn the function y equals x, right? I just have x come in, and I want y equals x at the output, but I have to learn it through this bottleneck function. What happens if I do that? Well, I have to, it's not going to be right? There's going to be errors. Right? So if I look at the output here, y hat minus x, it's going to be not 0, right? There's going to be, because you can't, right? But it will say, can I find the most important parts of x? And that's where a lot of unsupervised learning ends up doing some very clever things, because forcing the bottleneck forces you to find the important parts of x, and that can give you insight. Because now I say the network figured out for you what was the important part of the data. But this is very, very closely related to a technique in statistics called factor analysis, principal components analysis, all of which we'll get to later on. But these are important. One thing that is important to realize, I mentioned this early on, it depends on the encoding. If these are encoded as a real number, so if I were to do this, a bunch of inputs here to a single output there, right? Suppose this is a real number, and this is x1 to xn. I could encode here that real number. I could just say, let's call this, some value z. I could say z is e, and suppose that these guys are encoded as I don't know, 8-bit numbers. So I could say z is equal to xi times 256 to the ith power, some of those things, right? So if this has more bits than these guys, and a real number has an infinite number of bits, I can do an encoding here that completely captures these things, and I can decode them just by doing bit shift operations, right? And I could get x's out perfect. I could do perfect decoding. So that's not really a bottleneck, right? To be a bottleneck, you need some constraint either on the bits of these things or on the type of processing you can do here. Like, you don't allow this kind of encoding. Okay. And let's see, was there anything else? Oh, he does this thing on convolutional networks. We'll go through that. I can do that in a different, I can go through that at other times. That involves weight sharing. And I talked to you already about this issue of dynamic systems and LNL networks. So since we've run out of time, I will stop there. And I will hang out and answer questions. This is a very dense chapter. There's a lot of stuff here. And don't worry, we'll be coming back to lots of these things. But you will find that the book starts to accelerate from here. We're gonna be going faster and faster. There's a lot of material. So feel free to stop me when it doesn't make sense, and feel free to ask questions. Thanks.
Thank you.
Sure.
Professor, I have a question.
Sure.
So when we use the recursive function to calculate the delta n minus 1, because we already get delta n and we can use the delta n to update the weights. So when we calculate the delta n minus 1, do we use the updated weights or non-updated?
That's a very good question. Usually non-updated. You can, but usually people do the forward pass first, then the backward pass, then update everybody. But in fact, if you want to do the forward pass, one step of the backward pass update, then the next step of the backward pass update, that also works actually. It's no faster, but it will converge.
Is there any benefit or problem when we use the updated weights to do?
There are situations where it does work, where it can be helpful. So one of the things that was proposed, and actually Jeff Hinton's talked a lot about this. Suppose I've got a network like this, just a bunch of different layers going on. Now, and this is sort of whatever this is, Y3, and this is X1. So I'm going through that. These weights at the third level depend on these weights at the first level. So if I change delta W1, that forces me to change delta W3, right? Which then forces me to change delta W1. So these things interact. So something that people often will try to do is they will say, okay, let's fix this. We will hold W1 and then train W3. Just over and over and over again, right? We will just fix this. We'll say there's W2. So what we'll do is we'll say, X3 equals sigma W2 times sigma W1. Sorry, get those subscripts right. W1X. So I'll just do this as if these things are fixed, as if W2 and W1 are fixed. I'll just do that. And then I will just train W3. Delta W3 equals delta 3x3, right? And I will just keep training that, right? That's negative. And so you'll train this one, and then I'll fix that. Now I will hold W3, and I will train W2, right? And I'll just train this all the way till it converges. And then I'll hold that one, and I'll train W1 all the way till that converges. So there are sometimes there's advantages to doing that. Overall, it probably doesn't save you a whole lot of time, but it can lead to more robust network performance. So if sometimes these things will oscillate in funny ways, particularly as you get close to the optimum. And at this, what you're doing here is every single one is an LMS rule, which won't oscillate, like they'll converge. The other thing you can do is if you do that, you can train the individual networks layers using W star equals RYX, RXX inverse, right? You can do it in one step using linear regression, right? So in fact, there are sometimes by using different algorithms, you can do these in different layers. The original deep learning algorithm actually did things one layer at a time using an algorithm called the restricted Boltzmann machine, RBMs, which would essentially train one layer at a time as well. And each layer would depend on the others. If you train them one layer at a time, if I train, it's tricky because you still need to back propagate the errors down, right? So I still need candidate initial values for W1, W2, and W3. But I can propagate X all the way here. I can propagate the delta all the way back down to here. And then I can just train between these two layers using those X and deltas without changing the other weights. And sometimes that goes very quickly.
Okay.
Does that make sense?
Yeah,
there's a lot of options. And the problem with these things is that there's no right answer. And for the most part, there's no analytic, there's no real theory that tells you what the right answer is. These networks are very complicated. There was a theorem that showed that a multi-layer network is no better than a two-layer network. That's because the two-layer networks are universal approximators, right? Because this thing is a universal approximator, there's no point in adding more layers. That is a mathematical proof. However, empirically, people have found that often these deep layered networks can be smaller than a two-layer network that accomplishes the same task. We don't know why that is. These things tend to train much faster. So these train much slower, therefore require, in general, a lot more data. But once trained, the networks tend to be smaller.
What do you mean once trained, the network tend to be small? You mean
so if you have a fixed error, if this is network 1 and this is network 2, and I just want to look at the error. So I want to say y star minus network 1 of x. I'm going to look at the expected error of that thing. And I'm going to compare that to y star minus network 2 of x, right? And I want to say that these things are equal. Suppose that equals some error epsilon. This also equals error epsilon, right? And then I ask how many hidden units, how many of these middle layer neurons do I need? The multi-layer networks often require fewer hidden neurons than this to achieve the same error.
Oh, okay, I understand.
Yeah. So, but at the cost that the learning itself, the training, often is slower. Now, if you look at the way these things are often used in practice now, what people will want is that once you suppose I'm training a network to drive a car, right? I really only have to train it once. I need its performance to be really fast. But the training, I could spend 10 years training this thing. Yeah. So sometimes that's fine, right? Sometimes we say, look, it's okay for the training to be slow, but if I train a small network, my performance will be fast because I can calculate that thing really quickly. So sometimes that's exactly what you want. In other situations, you say, look, I just don't have that much data, and I really have to learn really quickly. This thing is to do online learning. It needs to be able to figure out things it's never seen before right away. So now you may say, I'm willing to take a big network in return for having very fast learning.
Okay, I understand. Yeah. Thank you.
Hi, Professor.
Yeah.
So I have a question is outside the course, just curiosity. So you mentioned that network with one hidden layer is a universal network. So basically, if you have network with one hidden layer, you can approximate any function.
Well, any smooth function, yes.
Any smooth function, okay. So I'm curious, is there so far people using theory to, let's say, give upper bound or approximate the number, how many neurons I need for the hidden layer?
There's been a lot of work. There's been a lot of work on that. It's a hard problem. For multi-layer networks, it's a very hard problem to solve. You can do it for two-layer networks. Where a lot of that work has been done most clearly is in the radial basis function networks, which we will talk about in a future chapter. But if you look at the radial basis function networks, they have there are two layers in this sense, but only the top layer is trainable. These guys are fixed. So what would be an example of a network that has this structure? Suppose this is x, that's y. This could be 1, x squared, x cubed, x to the fourth, x to the fifth, right? And so on. So now this allows me, so in this case, y is equal to sum wi x to the I, right? So that's a Taylor series, right? So this structure of network you can analyze, and you can say exactly how many terms do you need, right? Because we have bounds on the number of terms in a Taylor series that you need to approximate certain classes of functions. You could do the same thing. Suppose a slightly different one. We could have same thing, x input, y output, bunch of nonlinearities in the middle. And this could be sine x, sine 2x, sine 3x, sine 4x, and so on. Probably need the cosines in there too, right? These are fixed and these are variable. And now I might have the sum of, wi times the sine of I times x, right? So that's a Fourier series. So
Yes.
in general, you can solve it for situations where you have Wi phi I of x, and you know something about the properties of these phi i's, right? So you can put bounds on that case. The problem in these multi-layered networks is that phi I itself is not a fixed value, right? So that phi I itself is itself the network below. So now if we think about, what's the output here, that output is comprised of a bunch of things here, each of which we could write as, if that's x, as its own little network over x. I mean, this is the same x, right? These are the same thing. But the point is, you could think of these as being little network functions of x. And so that class is not well characterized. And it's not just that we have people haven't tried. It's just a hard class to characterize. It sort of defines itself. It's neither band limited, nor is it limited in terms of it doesn't have the same kind of bounded variation parameters. It doesn't have convergence parameters. It's just not well described, and it's not a linear. Most of this theory comes from this theory of linear Hilbert spaces. It's not a Hilbert space. So because it behaves badly mathematically, it's not easy to figure out. So that said, people do put bounds on these things, and they definitely try, but it's much easier to do in the case where the phi i's are a fixed set of functions rather than things that are variable.
Okay, thank you.
Sure.
Hi, Professor. So in terms of the generalization, I'm wondering whether different kind of testing, like the training parameter, would